And I'm gonna start us webinar. Start webinar. Oh, are you sure you want to allow the attendees? Yeah.
I'm going to start sharing my
screen. We could also do Google Hangouts in the future, you know, but then I'd have to download it. And
this is fine. I'm going to share the presentation screen, maybe.
Hey people. Hey, everyone. Let's see. Hi, guys. Hi. Chat room. Since you guys, for attendees that are here, just so you know, you can actually chat. I love Thomas raised his hand. So the raising hand thing basically means I have a question. We don't have to be that super formal here because we do have a small intimate group. So if you guys want to turn on your microphone, you could turn your video on. I think there's only a maximum of 4 videos at a time. So, but we can make this into like an intimate session, you know, instead of having it be like a super formally webinar-y thing. Thanks everyone for joining. Hi, Jennifer. So everyone, this is Alicia, which you may probably know her. Do you want to introduce yourself? I'll let you introduce yourself.
Sure. So I'm Alicia Frame. I'm the lead data scientist at Neo4j, and I work on the product management team, responsible for the Graph Data Science Library, which I'm super excited to tell you about today. Working with engineering to build the product, set the roadmap, and working with customers and the community to get people using graph algorithms.
Yeah, nice. So just a brief heads up for all you guys that are in here. I'll also post it in the chat just to make sure that people join late because it's literally 1 minute into the webinar. Some of this stuff is not necessarily publicly announced.
This is a secret preview for you guys.
Yeah, it's kind of secret preview-ish. So we ask that you don't go screen sharing and, you know, posting it places. In a couple weeks, when did you say, Alicia? Like a couple weeks or like a month?
So we'll have a press release probably the first week of April. And then we'll be doing a digital event, I think at the end of April, to do an official like big press marketing launch. But we'll have the press release out, I guess, April 2nd is about 2 weeks from now.
Mm-hmm.
And then it'll be generally known. So I'll be talking about the Graph Data Science Library, which is the successor to the Graph Algorithms Library. It GA'd on March 5th. So we're like into week 2 of general availability, which is very exciting. I'm going to talk today about how to use it, specifically at scale. We've done a lot of engineering work around supporting, you know, multi-billion node graphs and running graph algorithms quickly, reliably in production. And kind of what went into that, what are the tips and tricks for getting it to work, all that good stuff.
Awesome. So just a heads up for everybody here, if this is your first time using BigMarker, if it's not, you already know, just ignore this stuff. But there is a public chat room, which you guys see. Alicia, if you decide you're like putting your whole thing in your screen, and if you can't, can you see the chat room when you're?
I can. I've got 2 monitors. Okay.
And then there's also a Q&A tab there. If you have a question that you want to be saved for later or something like that, you can punch it into the Q&A section. The way you do that is when you type out your message, it'll give you the option to, instead of pressing send, to add the Q&A. And yeah, I think that you can also private message each other, which I don't know if you guys need to do that, but I'm just going to tell you a little secret. But yeah, I think that's it. So, all right, guys, enjoy. And I will talk to you guys after the presentation. And, you know, since Alicia's watching the chat, she can, I'll let you know if there's any like questions that are going to be raised hands in the middle of the.
You can shout at me if there's something really important. When I'm in person, I always tell people they can throw something at me. I don't know what the equivalent is online.
All right, here's what we'll do. If any of you guys want to ask a question, like using your voice, because like you can control your own microphone, you can turn it on your video or whatever. If any of you guys want to do that during the presentation, if Alicia doesn't mind that you're going to interrupt during the presentation, and if it's relevant for that, you can put your hand up and then just turn your microphone on and just ask. You can literally just turn your microphone on and ask. You don't even have to. Okay? Is that everybody good?
Okay.
All right, cool.
Let's get started. So Neo4j Graph Data Science. What I wanted to talk about today is what the heck is the Graph Data Science Library? You might have seen on the community forums or on user Slack, we said, hey, the Graph Data Science Library is in preview or it's been released. What is it? And talk a little bit about the changes between the Graph Algos library and Graph Data Science, the changes to syntax specifically around the algorithms and the graph loaders, and then spend the rest of the presentation talking about how to build scalable workflows for kind of large production graph algorithm use cases. So I like to kind of start off with just like, what is graph data science and how are we defining it? And like the official definition, this is probably in some of our blog posts, is that it's basically data science, but with graphs. And what we mean there is you want to use the relationships and the structure and topology of your data to make better predictions and decisions. So it includes everything from querying a knowledge graph, calculating statistics about your graphs, running graph algorithms, or building machine learning pipelines. And kind of the two places where we've seen the most traction and interest in our users is either in graph analytics, where you have a specific question that you want to answer, like, I have a graph, tell me which nodes are most important, or what are the communities in this graph, where you can say, this is the right algorithm to answer this question, and I want to execute this on my graph and directly use those results. So I want to say, how many communities are there? I run label propagation, and then I use the results of label propagation, and I say, well, this community number, I'm going to go do something with this, or I hand it off to an analyst. The other kind of more advanced side of that is when we talk about graph-enhanced machine learning and AI, and that's when you're training models using graphy data. So you have kind of your existing model building pipeline. Let's say you build your random forest classifier. You're just adding new features that you're extracting from the graph, either with queries or via graph algorithms to summarize the topology. And what we've really seen is kind of everyone that we have up and running in production using graph algorithms or graph data science is really starting in the analytics space. So they're using the graph algorithms to answer questions they couldn't answer before, like who's committing fraud, or I have a entity graph, I want to do entity resolution and figure out which are unique users, or I have a marketing problem and I want to figure out who do I send my marketing materials to get the most impact. And they're running 1 to 5 algorithms to answer those questions, and then the results are being handed off to an analyst who does some manual work with those. Where everyone wants to be is graph-enhanced machine learning and AI, where instead of saying, here's my question, I run this algorithm, you run a bunch of different algorithms to generate features, and then you use variable selection to figure out which features are most predictive, go build your machine learning model, and it's more accurate because you have relationships. What we do to support this at Neo4j is the new Graph Data Science Library. So probably, I think most of you are somewhat familiar with the Graph Algorithms Library that was originally developed by Neo4j Labs. It's been out in one form or another for about the last 2 years. We have an awesome book about it. A year ago, I joined Neo4j to basically take that lab's effort and turn it into an officially supported product. And I guess a week and a half ago, we GA'd the Graph Data Science Library, which is the successor to the Graph Algorithms Library. So what we've done is there's kind of 3 pieces in the GDS library. We talk about how it's optimized for analytics. So our engineering team has spent a lot of time developing custom data structures that are optimized for global traversals and aggregation. If you ever used the old Algos library and you remember like graph equals huge, or graph is, what was the other, heavy. Those were the different backend data structures. We've spent a lot of time optimizing the data structure, so there's only one to choose from. It's the right one. It scales. It flexibly subsets and reshapes your graph. The next piece is graph algorithms. So the Graph Data Science Library includes the majority of the algorithms from the old Graph Algos library. There were a few that were retired because they were broken. There are also some new ones in the GDS library. The product-supported algorithms in this library are all highly parallelized, and they're guaranteed to scale into the billions of nodes. So we're really focusing on providing robust solutions so that you can run your graph algorithm, your graph analytics on a production graph for an enterprise organization. We're also offering at the same time early access to dozens of experimental implementations. So I'll talk about this a little bit more later on, but we have kind of the product supported namespace, but we also have the alpha and beta namespace, which give you kind of previews into experimental implementations of new algorithms. And that's where you'll see basically things start off in alpha, and then as they mature in the product, they move up into beta and then into the product supported namespace. And then one of the things that I'm the most excited about is we've spent a lot of time on developer experience for the Graph Data Science Library. I think I used the Graph Algos library enough to know that there were some frustrations with the syntax, with inconsistency, with it wasn't always intuitive. You could specify the same thing in many different places and get interestingly incorrect results. So we have spent a lot of time on simplifying and standardizing the API. So you can subset, reshape your graph, run your algorithms. It's intuitive. It's as customizable as you need it to be, but it's simple and straightforward to run. And then we spent a lot of time on documentation, training, and examples. So getting started is easy. I'll have this on the reference slides at the end, but we have a browser guide to get folks up and running. We've got a sandbox for graph data science. We've got a lot of materials you'll see coming out for training in the next couple months. So we want to make it easy for everyone to use Graph Algos in the Graph Data Science Library. And then the big piece here is it's all product supported and being actively developed. So we have a team of 8 engineers who work full-time on this. We're putting a lot of engineering resources into providing folks with the data science library that they need. So what the heck is in this GA release that I keep talking about? This is kind of the summary slide. When we talk about algorithms, we have 48 different algorithms across 3 tiers of support. We have 5 production quality algorithms. So these are the ones that we guarantee will scale. They're parallelized, optimized implementations. We have 2 beta algorithms, and we have 41 alpha algorithms. And this is the majority of the old labs algorithms. And they all support 4 modes of execution. So before you had streaming, and if you didn't specify anything, it would write to your graph. We now also include stats and estimate, and I'll talk a little bit more about that later on. For infrastructure, we now have a single scalable, flexible in-memory graph structure that you use to execute your algorithms. So if you've ever seen the graph.load command, what that does is that takes your underlying transactional Neo4j database, reshapes it into the in-memory graph structure that we use to execute the algos. We spent a lot of time decreasing the memory footprint of that, fixing it, making sure it's as big as it needs to be. The only limit right now is really the amount of memory you can get your hands on. API, I talked about this already, standard simple API supporting production scale workloads. And then a lot of work has gone into documentation. So those are kind of the 4 pieces of what's in the GA release. And I think one question that I've heard from our field team is this actually any different from the Graph Algos library? And the answer is yes. So at one point in time, there was a 2 billion node in-memory graph limit. That's gone. We now have a single native graph loader that's optimized for memory footprint and speed. So as much heap as you can give it, you can store as many nodes as you'd like. Support for multiple relationship types. So you can now see and store and recall multiple relationship types in your in-memory graph. We also support relationship aggregation. So you can flexibly deduplicate or summarize relationships in your transactional graph when you load it to the in-memory graph. And we also allow you to combine node labels without using the cipher projections. You will hear me say this several times in this presentation. Cipher projections are super flexible, but they're also quite slow. We want to make it fast and flexible to use the native graph loaders. So we spent a lot of time making sure that that's expressive and able to support kind of what common work patterns we see. We've really shifted the workflow into named graphs and graph catalog operations. So probably if you've used Graph Algos before, you're used to a workflow where you type something like, call algo.pagerank person knows, and then you hit enter and it calculates and it writes it back to your graph. That's really good for a one-off, but if you think about running something into production, when you call algorithms that way, you have to load the data into the in-memory graph, execute the algorithm, and delete it. If you're running multiple algorithms in an analytics workflow, you probably don't want to keep reloading and deleting your graph. So what we've done is we've pivoted towards you load your graph once using the flexible graph loaders, and you load kind of all the data you need. You execute your algorithms against that in-memory graph, and then you delete it. And often the slowest part of algorithm execution is that graph loader step. So we've pivoted so you're only doing that once or as few times as you need to, instead of kind of constantly reloading. So we spent a lot of time kind of pivoting the library towards that type of workflow. All of the product algorithms have been re-implemented for improved performance and scale, so rebuilt from scratch, bug fixes across the board, and there's a complete API overhaul with new consistent syntax and error messaging. So I'm going to give you a lightning fast tour of how to use the GDS. I want to talk more about the workflows, but I realized it doesn't make a lot of sense if I don't explain it, like what the syntax looks like first. So bear with me. Super exciting. All the algorithms in GDS now follow the same syntax with the same consistent configuration parameters across the board. It pretty much always looks like call GDS dot tier if you have a tier for your algorithm, dot name of algorithm, dot execution mode. You can use dot estimate, and then you provide it with the name of your graph or the configuration. And you just have to remember this in order to run Algos. Walking through what these different pieces are, we have tiers of support. So I already talked to this a little bit. Product supported means they're supported by product engineering. If something is broken, we fix it right away. They're covered by like our enterprise support agreements. They're supposed to be stable, scalable, fully optimized. These are all called by just call GDS.algorithm name. So this is PageRank, Louvain, label propagation. Let's see if I can remember the others. Node similarity and weakly connected components. Beta algorithms are candidates for the product supported tier. So what this means is we've spent time optimizing them and building them up. But what we haven't done yet is maybe they're missing some documentation. Maybe they're missing one of the different execution modes, probably stats. But we're actively developing it, and it will become product supported probably in the next release. And so right now, I think K1 coloring and modularity optimization are in the beta namespace. And then the alpha algorithms are the experimental implementations. These are kind of the least stable, and they can be changed or removed at any time. This is basically where things get put to test to see what the traction is. And then as we see adoption, those mature up into the product. But we wanted to keep everything available to all of our users instead of saying, well, these 5 are the 5 we finished. So we have 3 tiers of support. Different execution modes. So this is pretty exciting to me. Probably most people on this call who've used the Algos library have forgotten to specify .stream and accidentally written to their graph. So right now we have kind of the 3 core execution modes. So .stream is still there. Streams your results back as Cypher result rows. Now we have .write. So instead of writing to the graph being the default behavior, that's quite slow. So we want you to explicitly say .write, and you specify a write property. And this writes back to your graph. And then we have .stats. So this will return statistics about the algorithm output, things like percentiles and counts. And so this is a good way to say, like, I want to run this algorithm. Before I write it back to my database, I want to see if the results make sense. I'm going to run Louvain. I'm going to pull back the stats, and I'm going to look at the percentiles and see if they're reasonable before I save all that data. And so this is kind of a nice trick to check your work before you commit to using it. In the next release, so the 1.1 release, which should be coming out, there should be a preview by the end of March. We will also support .mutate, which will let you update the in-memory graph. And that's pretty exciting. I might talk more about that later. Then we also have .estimate. So estimate is really important. If you've used GDS or graph algos on a large graph, you've probably out of memory your database and knocked it over. .estimate tells you if you have enough memory to run the algorithm before you try to run it. So it's just like .estimate with graph catalog operations. It's call gds.pagerank.write.estimate. Will tell you how much memory do you need to actually execute that algorithm. And this is only supported for the production quality algos, so the main namespace. But as things graduate up, we support .estimate. An important thing to be aware of, anonymous versus named graphs. So when I talked about before, probably a lot of folks are used to doing, call algo.pagerank person knows. That's an anonymous graph. So it's loaded at the same time as the execution of the algorithm. Named graphs are loaded separately with a name so they can be referenced. So that's when you call an algorithm, and instead of referencing the nodes and relationships, you pass it a graph name. And what we're recommending is for scalable workflows, moving towards using a single named graph, loading it once, and then flexibly running a bunch of algorithms across it. Cool, so that was super lightning fast. What is going on with the algo syntax? Now to quickly cover the graph loaders. Why do we have this graph.load step anyways? Why is it there? The kind of technical explanation is that executing graph algorithms is hard. We need the right data structure to do it. So if you think about transactional Neo4j, like the core database, it is a doubly linked list. And this is optimized for fast local reads, it's mutable, and it's queryable. But when we think about like running an algos workflow, you need to kind of iterate over the entire graph many, many times. So we actually store our data, or we reshape the transactional data into an adjacency list. It's currently immutable. It's optimized for these global traversal operations, and it reads writes from the Neo4j database. But what this means, because we're not executing on the core database, is we can flexibly reshape your underlying data and create and manage multiple analytics graphs to support different workloads. So I only need to look at this part of my graph for this algorithm. I can load this up via the graph loader, I can reshape it, I can change it, and then I can save my results back. This is kind of the schema of how this works. So you have Neo4j, you read your projected graph via the graph loader into an in-memory graph, which is the adjacency list structure. The algorithms are all procedures that execute on top of that. And then you can either stream the results out or write them back to Neo4j. Coming soon, you'll be able to also update the in-memory graph. So analytics graph management, now that we're telling you that you should create graphs, super important to know what to do with them. You can create graphs, you can track graphs, and you can remove graphs. Important not to forget about removing graphs. They will stick around in memory until you remove them. And if you create dozens of in-memory graphs, you will eventually knock over your database. And I am saying this from experience. So when you create graphs, I already talked a little bit about named versus anonymous graphs. So the named graph is loaded once with a name, and it's used by multiple algorithms. So I load my graph into memory, and then I run PageRank, and I say, call gds.pagerank my graph. And it knows that that's already been loaded, and it executes against that. And the anonymous case is where you create the graph, execute the algorithm, and delete the graph in the same step. The other dichotomy in the graphs to think about is the native versus Cypher projections. So these are, the native projections are when you use something like graph.load person knows, and you're referencing the node labels and relationship types, and we can load directly from the data store. So that's very fast. We can do it in parallel. If you are trying to run something scalable and repeatable, native is kind of where people start. The Cypher projections use a Cypher query to populate the nodes and relationships, then get put into the same data structure for the analytics graph. This is still bottlenecked by Cypher. So Cypher is great, Cypher is expressive, Cypher can sometimes be slow. So basically there's a trade-off where native is less flexible, but lightning fast. Cypher is more flexible, but not as performant. So kind of be aware of those two trade-offs. The syntax for this is pretty straightforward. Call gds.graph.create, and you specify a graph name, a node projection, so the node labels and node properties you want to load, a relationship projection, which are the relationships and relationship properties you want to load, and a configuration parameter. Generally speaking, you're just going to be setting read concurrency. You don't have to set this, but for some use cases, if you have multiple people, you may want to set your concurrency. What this actually looks like, it's easiest just to walk through starting with node labels. So for nodes, you specify there's a shorthand and a longhand form. Shorthand is easy to understand. It's just gds.graph.create and your graph name, your node label, your relationship type. The long form is you can specify a node label that you want to call it in your analytics graph, the underlying node label in Neo4j, and the properties that you want to map from Neo4j. So you can load into memory a node label and properties associated with those nodes. And right now, you can combine multiple nodes to be represented in the same node label in the in-memory graph, but you can't load two node labels and distinguish them. They'll just be combined. Coming in 1.1 node, there will be support for multiple node labels in the in-memory graph. Relationships are a little bit more complicated. There's a little bit more going on here. We talk about support for multiple relationships. So now in the GDS, you can load multiple relationship types. So you can load as many relationship types as you want. The reason you might do that is, let's say you have your Game of Thrones graph, you have person interacts with, person battles, person loves, and you could load those three separate relationships once. And then when you run your algorithm, you could say, I want to use my Game of Thrones graph that I've loaded into memory, and I want to use the loves relationship for PageRank. And now I want to use the knows relationship for PageRank and see how it differs. So it lets you kind of quickly run a bunch of different algos on different flexible configurations. For this, so you load the relationship type, the orientation. So this is basically direction before, aggregation. So how you want to combine multiple relationships or if you want to combine them, and the properties associated with that. So any data like weights that you want to load into memory. I'm not going to go into this any further, but I will have some links to the docs at the end, or if people are interested, I have a much longer deck that goes into this. So cipher graphs. Native graphs are fast, cipher graphs are flexible. They're okay to use if you're kind of in experimentation phase and you're trying to pick a data model. If you don't really care that much about performance and repeatability, or if you have a small graph. And the syntax for this is GDS graph create cipher. And otherwise, it's basically the same. You have the graph name, the node query, the relationship query, and the configuration. And so just an example of what that looks like, you have, I'm creating my graph, I'm matching all the people nodes, I have a relationship that I want to project, and then I'm going to have the first person as the source and the second person as the target. If I want to change directionality, I just do this in the second query. So if I want to reverse the direction, I might say ID P2 as source and P1 as target. Or if I want to have it undirected, I could just have the query be undirected. Cool. So that was lightning fast, drinking from the fire hose overview of the syntax. Let me check. There's a little red light on the Q&A. Aha, I see questions. So I will answer these before I go on. So is there a rule of thumb for graph size and available memory? It's all done on heap. There's not really an easy rule of thumb. There is a long formula that I could share on graph size and available memory. The easiest thing to do is to use the .estimate function, so gds.graph.create.estimate. The other thing you can do is it's in the docs, is you can do estimations for fictitious graphs. So if you don't know how big your graph is going, you don't have your graph loaded yet, but you say, I want to know how much memory it's going to take for 1 billion nodes and 5 billion relationships. You can just pass node count and relationship count to the graph estimate function to come up with an estimate of the memory for that fictitious graph. 4.0 compatibility, not yet. Right now we run on 3.5.8.2 to whatever the most recent 3.5 release is. We will have 4.0 compatibility targeting the end of April. So we're looking at having a preview release of a 4.0 compatible jar probably the last week of April, GA the first week of May. Can you work with a subset of the graph you've loaded into memory? Yes. So if you've loaded multiple relationship types into your memory, you can specify when you execute the algorithm which of those relationship types you want to run over. As soon as we roll out multiple node support, you can do the same thing for the multiple node labels. So you can load more into memory than you plan to execute on. And then how do we know which ones are most helpful and we would like to see implemented? Tell us. I do read and respond to things on the community forum. We also kind of have an ongoing early adopter program with customers who use the Graph Algorithms library, who are keen to get started, scale up, and we work really closely with them to say, okay, what is it you need? What are you working on? What meets your requirements? And let's scale this algo up for you. So I can say right now, triangle counting, betweenness, and degree centrality are ones that are in the candidate list to be worked on. We also have a new algorithm in the pipeline for community detection with multiple community labels. So a node can belong to more than one community. These are based on feedback we've gotten from customers in the community. So tell us, we're listening. We don't have any way of spying on which algos you call, so you have to tell us which ones are useful. Now I will go back to presenting. So how do I put this all together and actually use this? The topic of this webinar was graph algos at scale. I'm going to spend a little bit of time talking about the other ways you can use them, and talking about deciding what's the right workflow for what you're trying to do. And so I've talked about already in the presentation, I touched on a cipher graph versus a native graph, and a named versus an anonymous graph. And really for all of these, there's a trade-off between flexibility, speed, and ease of use. So I kind of like to talk about this like you have your super flexible cipher graph, you have your really performant native graph, you have your reusable named graphs, and your really easy to use anonymous graphs. So if you're starting off with like, I want to teach someone how to use this library in 5 minutes, teaching them to use an anonymous graph using a native projection is the easiest thing to do, right? That is called gds.pagerank .write and passing it, person knows. You don't have to think about all of the infrastructure. It's easy to get started and get results, but it's not very expressive. When you talk about like starting with proof of concept, so I have a graph data science problem. I want to figure out what's the right data model. What am I trying to do? I'm just doing quick proof of concepts. Often we see people moving to the anonymous algorithm calls using the cipher loader. So that's where you can flexibly kind of test out different graph shapes. And it's not performant, but at this step, you're just kind of saying, well, what do I want to do? Once you get to workflows where you're kind of trying to do something repeatable, that's when you move over to the named graphs. If you don't have tight time requirements, or if it's something flexible where you're kind of doing one-offs, we do see people using the cipher projections and a named graph. So that's loading a graph into memory using cipher, but it's named so then you can reuse it. And then when you're at kind of your most performant, I have what's our biggest customer? I think we have someone with a 20 billion node graph in production right now that they need to finish executing connected components on in under 24 hours with a bunch of other stuff going on. They use a native named graph. That's the most performant. It's the most reusable. That's where you end up when you need performance. And that's what I'm going to spend time talking about in the next couple of slides. So education and quick demos, anonymous graphs, native projections. It's how you get started without worrying about the syntax. When you're talking about a production workflow, you probably don't want to use this. It's quick, but it's not robust. It's not repeatable. And also you lose the benefit of separating out graph loading from the algorithm execution. So it can make it a little bit harder to debug what's going on. When I've done hands-on trainings, if you do the graph load step separately from the algorithm execution step, you can see what you've loaded into memory. And we find that about 2/3 of the problems people run into is a mistake with like the relationships or the nodes they're loading. And when they load that in first, they can see the statistics and it's like, oh, I loaded no relationships and 2 billion nodes. I know why this didn't work. And separating those out makes it easier to see this. So only use the anonymous native combination when you're doing kind of quick teaching. We talk about using cipher projections for prototyping. With an anonymous graph, it's good for just testing out different data models, checking the syntax, or if you only need to run one algorithm. And it's good with a named graph if you need to run multiple algorithms, but you're not quite as sensitive to speed, and you can't modify your underlying data model for whatever reason. But again, this is slow. So often when I have someone come to me and say, I hate graph algorithms, I hate graph data science, it is slow. I say, show me what you're doing. And they're using a very complicated cipher projection. So when you want speed, don't use cipher projections. So this is my favorite form, like infographic. I spent entirely too much time making this. How do you use GDS in production? And so we talk about going from question formulation, checking that you have enough memory, loading your graph, executing your algorithms, cleaning everything up, and analyzing it. And I'm going to walk through each of these steps with kind of a motivating example. And hopefully this will make some of what I've talked about a little bit more hands-on and easier to wrap your head around. So let's start off with question formulation. So with question formulation, we're talking about defining the problem you're trying to answer. I've had many people come to me and say, I would like to do graph data science. And you say, well, what do you want to do? And they don't know. You need to have a problem up front because that's going to drive what your data model is, what algorithms you're choosing, and kind of how you proceed. So start with kind of the problem space. Are you making recommendations, finding anomalies? Once you know what you're trying to answer, you can match that with the right set of algorithms. So like really commonly we see people want to make recommendations. Oh, I'm going to use similarity or community detection. I'm looking for anomalies. I'm going to use centrality. So start with your problem, match it to an algorithm. And then once you've chosen your algorithm, then you need to think about modifying your data model for the algorithms you want to use. So most of the graph algorithms expect a mono or bipartite graph. So similarity will expect a bipartite or multipartite graph. All the others expect a monopartite graph. So that means one node type and one relationship type. For performance, you may modify your data structure to reflect this, to make this easier so you don't have to use a cipher projection every time. You may also think about things like, okay, I need to use different labels or relationships to use a native graph. So I need to do a data split. So I'm going to call one set of relationships test and another train. You also want to think about using weights or seeding. So if you're going to be running the same algorithm every day, after, let's say you load 10% new data every day, and then you rerun your community detection algorithm. Well, then you want to use seeding so you can save your results from the first time and only run on the new data. Or if you're running a lot of the centrality algorithms, weights are really important in calculating these things. So think about the data you need to have in your data model to run your algorithm. So I like to kind of use this example of drug discovery. My background is kind of in the life sciences. So this was several years of my life in a previous job. How do you find new target genes for diseases? And this is just a toy problem, but let's say you have a graph. This is from het.io. You have genes, diseases, and chemicals. You've got information about the pathways and the cellular function of those genes. You have information about side effects and pharmacology for different drugs. And for diseases, you have information about anatomy and symptoms. And this is kind of the graph that you start with. And so you start with, what is your motivating question? And for this kind of toy example, I'm going to say, well, I want to find new genes that could cause a disease. So these genes should be associated with a disease, but there's no edge in my graph right now. So starting with that question, you can quickly choose some algorithms. So I said, well, node similarity could tell me something important. So if I find a gene that's really similar to another gene that I know is associated with the same disease, maybe that's a new target. Or I could use something like community detection. So find communities of genes that interact frequently with each other. And if I find a gene that's in the same community as a gene associated with my disease, but not yet associated, maybe that gene is relevant to my disease. And then maybe I want to do some data QC. So I say I want to use the centrality algorithms to make sure I'm not choosing really highly connected or really important regulatory genes. So if you think about how the body works, if you knock out something like ubiquitinase or a metabolic enzyme, you will not cure the disease, you will just kill the patient. So you want to say, I'm going to use centrality to filter my results. And so now I've said, okay, I know my question, I know my algorithms, and now I have to think about reshaping my graph. And so what kind of graphs do these algorithms expect? So for node similarity, you're really looking for a bipartite graph. So I have my genes and I have the things that they're similar to. The other two, community detection and centrality, expect monopartite graphs. So now I want to go back to the graph that I had and think about how I want to modify the data model. And so the simplest thing is I can say, well, I want to look at my genes and what they're similar to. So I want to keep pathway, function, drug, and disease. So those are things that could be similar to, and here are the relationships that were in the underlying data that I want to consider for node similarity. So genes can be similar to each other based on common diseases, common drugs, common pathways, common functions. Pretty straightforward. And then I want to say, well, I really want this to be performant. I don't want to use a cipher projection. I want to modify it so that I can run this over and over again. I'm going to add some monopartite relationships around my genes so that I can run community detection and centrality. So I'm going to go in and I'm going to add, the same pathway, same function relationship for genes to other genes. I can add these genes treat the same disease. These genes are same disease based on a common drug, or these genes are targeted by the same drug. So I want to go in and I want to take that kind of raw data model I started out with, where I had everything in the kitchen sink, and kind of fine tune it just to what I need for the algorithms that I want to run. So step one has been done. We figured out our question, we figured out our data model, we figured out our algorithms. Now that we know that, we need to think about, how is my database configured, and do I have enough memory to run the algorithms I've chosen? Get an idea of how long this is going to take, and think about if there's anything I need to change. So for memory, that's pretty easy. You can just run GDS graph create estimate. And the star syntax is if I were to load the entire graph into memory, all relationships and all nodes. It's not a best practice, but that gives you kind of your worst case, the most you could load into memory. Generally speaking, and doesn't fit as well on this slide, you would type out specifically the graph that you wanted to load into memory, stick a dot estimate after that, and that'll give you lower and upper bounds for heap consumption. You can also call estimate on your algorithms. So you can say, I want to run PageRank. That's one of my centrality algos. I'm going to say, I want stream mode. Let's estimate how much memory that'll take. After you've checked that, compare that to what you have. If you don't have enough memory, you probably need more. In 1.1, we will be introducing some guardrails. So if you absolutely don't have enough memory, even in the best case, we will throw an error instead of letting you knock over your database. But right now, you have to check yourself. There's no really easy way to check how long something is going to take, but we do know, relatively speaking, which algos are faster and which are slower. So node similarity is the slowest algorithm in the library because it is a pairwise comparison across the entire graph. You can use a named cipher graph to load a subset of the data and benchmark how long it takes, given the concurrency settings that you have. Or you can use the graph.generate function to generate a random in-memory graph of the specific size you're going to run over, and run against that to get kind of a ballpark of how long is this going to take. If you want to make it faster, if you need to change anything, so you have to have enough memory to execute the algo. This is kind of the hard limitation. The upper bound is a guess. So if you are in the range and you can't get more memory, try to execute it. If you are below the lower bound, it's probably not going to run. More threads will give you faster algorithm execution, both for the graph loading step, which is roughly linear, as well as for the algorithms. Some scale better than others, so node similarity, the more threads you throw at it, the better, whereas PageRank kind of tops out, depending on your graph structure, at like 16 to 32 cores is kind of the optimal. And then consider pre-processing to break up or parallelize your work. So when we said, okay, node similarity is really slow, I have a billion node graph and I would like it to finish someday, I might run weakly connected components first, figure out how many subgraphs I have, and then run that analysis on each of those. So kind of use this step to iterate on what you're doing and see if you can get acceptable performance. Once you've done that, load your graph into memory. So this is the graph.create function. You're going to load your analytics graph. You can't skip this. We just want to minimize the number of graphs we load into memory. Every graph you load into memory will take more memory. So an important question is, what's the minimum number of graphs I need to load to answer my question? So the way I like to do this is I start with, what are the algorithms that I want to run? What are the nodes those algorithms are going to execute over, and what are the relationships? So here I have node similarity, I have weakly connected components, Louvain, and PageRank. And so node similarity runs on a multipartite graph of genes with pathways, functions, diseases, and drugs, whereas the monopartite algorithms are just going to run on genes, but each one is using a different subset of relationships. And as I said before, we can tell relationships apart in the in-memory graph. So I can load same pathway, same function, same disease, same drug, and then I can execute on my in-memory graph and say only use the same drug relationship, but all of the nodes will be combined. So if I think about this, I can kind of sketch out, what does this look like? So with one graph, I would just put all of my nodes together into the node projection, and they would all be combined in memory. And then in the relationship projection, I would have all of the relationships that I had listed out on this previous slide. So throw everything in the kitchen sink into the in-memory graph. And then if I have two graphs, I'd load one graph just for similarity because I have a different set of nodes that I'm looking at. So I'd have gene, pathway, function, disease, and drug. And then I'd have the relationship projection. So participates, associated, downregulated, upregulated, to measure just similarity. And then I would have my community detection and centrality monopartite graphs where I'm loading gene and then these monopartite relationships. So what are the pros and cons of this? So if I load everything into one graph, I can track different relationship types and selectively use them. So I could tell the difference between the same function relationship and the associated relationship. But I can't tell the difference between the node types. So I'll end up running centrality and community detection on a bunch of disease, drug, pathway, function nodes as well. And since these aren't connected or relevant, they're a different node type from my monopartite relationship, that will throw off my results. And similarity is slow, so it's often best to try to break up your workload. The flip side, if I use two graphs, I'm loading the right data for each class of algorithms, so it's less memory, and I'm not running over nodes I don't need to go look at. And I can write the results back from community detection or centrality and then use that to influence running similarity. So the idea here is if I use two graphs, I'm using a little less memory. I'm still able to reuse that monopartite graph for all of my centrality and community detection algorithms, but I'm only running on the right number of nodes. So for this use case, you'd say, well, really two graphs are the best choice for this workflow. So what this looks like is you'd say, looking at the monopartite graph for centrality and community detection, you'd say call GDS graph create. I'm going to call it monopartite graph because I'm being super creative. And I'll load in my gene and then the relationship types I'm interested in. And this is actually the syntax for the library. I'm using a shorthand, somewhat less expressive version so that it fits on the slide. Then for my similarity graph, I'd be loading in my gene and all the things that I'm measuring the similarity to. And then what I'm able to do is I can kind of flexibly reshape my relationships a little bit. So I mentioned before we have aggregation and orientation. So let's say I want to use participates as a relationship type. I want to use a single aggregation, so I only use the first relationship that I see. But I can take disease and I can combine two relationships into one, three relationships in my transactional graph or in my in-memory graph into a single one that I'm seeing for the algos. And I can specify the orientation. So I'm saying reverse, etc. So you can do a lot of flexible reshaping even with the native graph loader. And so that's it for this one. So we've got our graph in memory. Time to start executing algorithms. So there's three things you can do. You can do stats, stream, and write. Stats returns summary statistics about the results without writing the data to the database. So this is usually the one that I recommend starting off with. So it helps you see if your calculations make sense. So let's say you're running PageRank. If you run .stats and you see that all your percentiles are 0, something is wrong. If you're running community detection and you find that every node is in its own community, you want to change how you're calling the algorithm. That stream will return all the results as a stream. This is usually useful if you're using the results elsewhere, so like in Python or for some kind of machine learning pipeline. And then .write will write your results to the Neo4j database. This is the slowest of the three modes, so try to only run write once you know that your algorithm makes sense. So this is the thing I want to store in my database, then you want to write it. I see a question. I will talk about this later. So back to running your algorithms, centrality and community detection. So this is what I talked about running on the named graph. So I'd say call GDS PageRank write, and my named graph is the monopartite graph. And someone asked before, can I specify which relationships in that in-memory graph do I want to use? I can specify this right in the algorithm call. So I'm saying run it on my named monopartite graph, but only run it over the same pathway relationship type. And I want to write it to the pathway PageRank. And then I could run this again and run it over the same disease relationship and write that as a different property. I can do the same for Louvain. I can run monopartite graph on the same pathway relationship and write that to a community. So then when I am loading, so yeah, I run it over different relationships to see how it affects the results. And you can just name different properties if you want to compare these later on. If we remember back to the original big picture, we had write and reload. So there's a double arrow. So it's not just graph create to write. Sometimes it's you write back to the database, you load a new graph into memory. So community detection is fast, similarity is slow. We don't want to run similarity on the whole graph. We want to save calculations. So maybe I'm actually looking for genes associated with multiple sclerosis. My question isn't that open-ended. So I can say I want to find all the genes associated with multiple sclerosis. I want to see what community they're in, and I'm going to label that community multiple sclerosis genes. And then I'm only going to run on that one labeled community. So what I'll do then is I'll say, create my graph using now I've written back to the database and I've labeled them MS genes. And I have pathway, function, disease, and drug. I've got all my syntax to load it in memory. Once I've got that, I can run node similarity and write my monopartite graph result back to those genes of interest. And then I've run this much more efficiently on just the subset that's relevant to me. Once I've finished up with that, the final step is cleaning up. Don't forget this. I have forgotten this and wondered what was wrong with Neo4j. GDS.graph.remove. I need to update this slide. And drop the graphs that you've already loaded into memory. You need to double check if you're like me, and sometimes you call graphs test1 and test2 and test3. You can use the graph.list feature to see all of them. Once you've cleaned up after yourself, then you can data science. So this is the final step we talk about, where maybe you're doing manual review in that analytics use case, where we talked about handing off to an analyst who's going to say, look at everything in a community by hand. Maybe it's a scientific expert, and they'll manually choose what's interesting. You may be transitioning this into some kind of visualization. So we have a new sandbox up for Bloom and graph data science, where we give examples of how do you visualize the results of the algorithms and what do you do with them? Or are you using those for some kind of model building exercise, where I'm now going to pull these properties out and I'm going to put them into some kind of machine learning pipeline as new features. So kind of once you finish this workflow of I've I've figured out my data, I've figured out my question, I've reshaped my graph, I've loaded it into memory, run my algorithms, cleaned up after myself, then you get to do your fun data science work. And so that is that. There was a lot to cram into 55 minutes with time for questions. But if you have any questions or you need resources, I've got links, probably most relevant here. If you want the GDS, it is available on the Download Center right now, 1.0.0. You can also, in Neo4j browser, type play graph data science to get a nice walkthrough that has examples of the syntax and of all of kind of different ways and kind of nuances to call in algorithms. We have 2 sandboxes up, one that's basically an extension of the browser guide using Graph Data Science Library, and then one using Graph Data Science with Bloom. The documentation is up, it's live, and our code is open source. You can go to github/neo4j/graph data science. If you run into problems, you have bug reports, you have questions, our GitHub is actually the best place to put those issues. We check that. It automatically goes to our team's Trello wall. We prioritize stuff from there. So check it out. With that, I will turn to the question.
We do have some questions, but I want to give people the option to be able to just turn on their microphones and just have a conversation. If either of you guys, Nathan or Lavanya, if you guys want, I know you guys had questions, and if anybody else here, you want to turn your mics on, or I guess we could just walk through the questions. But if anybody does, you could just literally turn on your microphone and we can have a conversation. Could ask questions that way. So do you want to answer Nathan's question first? It's shorter.
Yeah. So separate instance for GDS, separate Neo4j for GDS versus production. Do you mean like you have a transactional workload happening on a causal cluster and then you want to run a data science instance dedicated for analytics? Or are you thinking like, I have a prototyping machine and I have my production machine?
Okay, while he's writing it out, why don't we go to the next question, I guess.
I think, I'm not sure it's a question. Lavanya raised using a different term instead of monopartite graphs. It is a monopartite graph. You need to create the edges to create it to use a monopartite projection. I don't think we want to coin new terminology, but it's an interesting way to think about it instead of calling it monopartite, calling it an induced graph. But all of our documentation is monopartite. Graph data science comes out of graph theory, so we try to stick to the academic terms. Maybe Nathan fell asleep. Sorry.
Oh yeah, there's a chat window.
Oh, aha, I need to bounce back again.
Yeah, we can start asking the questions in the chat window just to make it easy.
Okay, so if the GDS loads are expensive, how do you schedule them? So the GDS loads are expensive. The most expensive step is actually usually write back. What we've seen in production workloads is basically they add new data, load the graph into memory, execute, write, and then remove the graph, repeat. The way that they're handling kind of new data coming in is they're using seeding for all of the functions that they call. So you run it once. Let's say I run weakly connected components on my data. I save those components, and then the next time I run my workload, I use the seeds, I load those into memory, and then I'm only identifying communities on the new data or if they've changed on the old data. And then I only have to write back on those new nodes. And it doesn't save you on the load, but it saves on the calculation and the write back step. And because write back is actually the slowest, that's a big performance improvement. And so that's how you can do, the tons of billions of nodes workloads in kind of a reasonable time frame. But in general, when we talk about GDS, most of this is intended for single user. So don't try to load many large graphs into memory from multiple users at the same time. We kind of think about it like a sequential operation. And the important thing to remember is when I talked about we're reshaping the data into the in-memory graph, they're not synced. So if you change your underlying transactional data, it's not synced in the in-memory graph. So we have the snapshot that we load with graph.load. We execute on that snapshot, and then the write back just goes back to those node IDs in the underlying graph. So you have to reload when data changes. So you kind of have to do it sequentially. Cool.
Cool. Does anybody have any other questions? If you need time to write it out, you can put the little hand raise icon next to the emoji, and that'll give you like a moment. We'll know that you have a question coming. Alicia, that was very thorough. Very good presentation.
It was a lot of information. I'm sorry.
No,
I was like,
good.
oh, they've never seen this library before, so there's a lot to explain.
Yeah, well, these are definitely the people that we want to know and understand it. So I mean, we want everyone to know and understand it, you know. But our ninjas, considering that they're active and always helping people and stuff now too, that's important.
For the ninjas community, keep your eyes out for the preview releases. Those happen 2 weeks before we GA, so we should have a preview with multiple node support, mutable in-memory graph, and the memory requirements built in, coming out March 26th is like next week. So test it out, give us feedback. We tend to do some updates between preview and GA, so look at those sneak peeks.
So people said they really enjoyed it. Thomas said, I want to find some more memory and start playing.
Or just a small data set.
All right, guys, thank you very much for coming. Thank you, Alicia, so much.
Thank you.
When there's a question in Q&A that I think is, yeah, another one. Lavanya just posted a question. Oh,
cool. I'll get back on that later.
Okay. I think it's not a question, more of commentary.
Yeah, that's fine.
All right. Well, thank you very much. Thank you, Alicia. I really, really appreciate it. And it's a lovely presentation.
Thank you, guys. Speak later.
All right. Bye, everyone. Let me stop the recording.